For our project topic, we chose harmonic motion. More specifically, we chose buildings' harmonic motion. Second-order differential equations provide an accurate framework of forces acting on a building during an earthquake. In this presentation, we will explore a real-world example of this and what that tells us about the effects on the building. Why can we use differential equations to model harmonic motion in buildings? Buildings behave similarly to springs, with mass, stiffness, and damping. They respond to ground motion that causes buildings to vibrate, sway, and oscillate, which can be represented by second-order differential equation model. Additionally, buildings store and release energy through damping forces such as friction, cracking, joints, and materials to produce an oscillating motion. Some of the basic physics equations that are used are Newton's second law of motion, Hooke's law. They both can be combined to form one expression for the motion of the entire building. The two basic physics equations discussed in the previous slide can be combined to form the following equation: m times x double prime is equal to negative b x prime minus k times x, where m is equal to mass, b is equal to friction, and k is equal to some sort of constant. This equation for vibration in buildings and bridges correlates to spring problems that we have seen in class, since there's mass, a spring constant, the elasticity/stiffness of a material, and a friction parameter.
So this second-order differential equation can be solved by separating the governing equation to a system of equations, which we know how to solve for. So we start with the mx double prime minus bx prime minus kx. We'll divide the m to the other side, so then we're left with x double prime, which is then equal to negative b over mx prime minus k over mx. And then we'll add both those terms to the other side, so then we're left with x double prime plus b over mx prime plus k over mx, which is equal to 0 now. And then we will also set y equal to x prime, so then that gives us x double prime is equal to negative b over mx prime minus k over mx, which is also equal to y prime. So then we get to this side, and then we get dx over dt, which is equal to y. And then bringing that over there, we get dy over dt, which is equal to negative b over my minus k over mx. So now for our specific variables that we have in our equation, we're going to use the Empire State Building as an example. Its potential mass is 317,514,659 kilograms, which is a lot. And then for our spring constant, which is our stiffness of our skyscraper, we're going to do 100 million Newton meters, 10 to the power 7. And then for our friction force, we're going to assume a static friction of 1, since we don't want any movement. So now if we plug it into our system of equations, we get dy over dt equals negative 3,114,818,805 over 317,514,659 y minus 100 million over 317,514,659x. And then pretty much dividing those to get a simpler equation, we get dy over dt is equal to negative 9.81y minus 0.315x. So that negative 9.81y makes sense because the y force should be the gravity acting on the building. And now we could take this equation and plug it into a matrix to solve and find our lambda values. So obviously we have our matrix. We take both our lambda values, subtract them from the two corners. So this will help us find our eigenvalue. And then by finding the determinant of that lambda matrix, we are left with lambda squared plus 9.81 lambda plus 0.315 equals 0. And then when we're solving for lambda, we use the quadratic equation to find our two lambda values of negative 9.78 and negative 0.06.
Taking these calculated eigenvalues, we can construct these two matrices and use them to calculate the corresponding eigenvectors, as shown. And using these eigenvectors, we can then plug them into the format for the general solution that we use in class and we've seen often throughout worksheets, shown here, in which we have the value x, which is the horizontal displacement, and the value y, which is the velocity, representing by the parametric equations. Using these eigenvectors, we can graph them and find the straight line solutions for this model. And because both of the eigenvalues are negative, we can conclude that the straight line solutions are converging towards zero, which means that with any given horizontal displacement and velocity, the building will always want to come to a rest and an equilibrium at its starting position, which makes sense that a building would only ever be in equilibrium when it's directly straight up and down and has not have any horizontal displacement. To classify equilibrium solutions, we're going to see two different types, and we're going to see underdamping and overdamping. And we can classify these by looking at the characteristic equation and finding the equilibrium points by taking the quadratic formula. Underdamping is going to occur when the value of friction B is less than the root of 4 times the mass times the stiffness K. For this, we're going to get an unreal answer, so the eigenvectors are going to be complex conjugates. For this, we're going to have to use Euler's theorem to convert them to real numbers, and our solution will be represented using sine and cosine. And because of that, we're going to see an oscillatory behavior where the horizontal displacement is going to oscillate between positive and negative values before settling at 0, 0, its equilibrium. Overdamping is going to occur when the value of friction is greater than the root of 4 times the mass times the stiffness. Here, the eigenvectors are going to be real numbers less than 0, that when plugged into the general solution of the form seen on the previous slide, we're going to get two eigenvectors that are straight lines that will be approaching 0. But because there's no sine and cosine, there will be no oscillatory behavior. The building will simply move from its horizontal displacement directly back to its equilibrium position at 0, 0 without overshooting it at all. So in conclusion, if B is greater than 0, i.e. some friction exists, the building will come to rest. Just like a spring would, that as long as there's some friction, it will either oscillate or just come directly back to its starting position. Looking at a specific solution, we can take an initial displacement of x equals 2, which gives us the value for the constants c1 and c2 as 1, and a starting velocity of negative 9.84. This situation is overdamped, in which the friction is enough to overcome the forces, so there will be no oscillatory behavior. As shown in the graph, the horizontal displacement never overshoots 0. It simply goes from 2 and quickly returns to equilibrium at x equals 0.
All right, so this graph here is showing us how much a building is shaking depending on the frequency of whatever's pushing it. In our case, it's an earthquake. And then how much damping this building has is represented on the graph. You've got the three curves here. You got the small damping, medium damping, and heavy damping. The sharp spike in the middle, like you can really see in the small damping curve, right over F0, that's when the earthquake's frequency lines up with the building's natural frequency. The building basically gets pushed at just the right rhythm to make it swing way more than it normally would. But if you add damping, those big counterweights or tuned mass dampeners that you'll see, the peak gets lower and lower. That means that the building doesn't react as violently, even if the earthquake's frequency is closer to F naught. So this graph is effectively just showing us why damping is super important and how differential equations help us to model all this and predict how much the building is going to move and ensure that it doesn't shake itself apart. So in this slide, we'll talk about the limitations because, unfortunately, like with all things, our model has limitations. Basically, these are the things that we simplified to make the math manageable for our model. The first thing we did was we assumed that the vibration is constant, which in reality isn't really how earthquakes behave. They fluctuate over time. And that will in turn change how the building is responding. We also assumed that the building is perfectly wind resistant, which is not going to be true depending on the design or materials that were used. And finally, we treated that spring constant, which represents how stiff the building is, as the same throughout the whole structure. But in real life, different parts of a skyscraper are going to flex and absorb energy differently. These assumptions are what helped us to use differential equations to model the motion, but they also mean that our results are ideal. If we wanted to make the model a little more realistic, we need a much more complex system of equations that account for all these variable forces and differences. So this slide here goes a little deeper into what can affect how a building vibrates, and also what our model doesn't fully capture. First, the materials matter a lot. They're very important. Like steel is super stiff, so it doesn't let vibrations travel through it as easily as something like concrete or glass is going to. That, again, changes how the building responds to shaking. Then there's the soil it's sitting on. If the building is sitting on some soft ground, it's going to move a lot more than if it's anchored into just a solid rock. We also assumed, for simplicity, that the mass is evenly spread throughout the whole structure, which isn't really true either. Some floors are going to have heavier equipment or more open spaces, and that's going to change how the building reacts. All these things affect the natural frequencies and damping behavior, and these are going to be key parts of the differential equation we use to model motion. So our equations give us a good starting point, but in real life, buildings are just way more complex, and engineers have to account for all of this when they're designing buildings for earthquakes. Okay, so now this last slide here is kind of the foundation of everything that we were modeling. We are treating buildings like spring mass systems, which was a little awkward at first, but it actually worked out pretty well with skyscrapers. The idea is generally just that the building has mass, stiffness, and damping. And when something like an earthquake pushes on it, it reacts just as a spring would. The motion that happens, that swaying or vibrating, I guess, can be modeled using a second order differential equation, which comes from Newton's second law. Newton's second law tells us that force equals mass times acceleration, which can then be combined with Hooke's law, which is what relates force to displacement through the spring constant, to get the equation that we need. Now, the big thing to watch out for in all of this is resonance. If the frequency of the ground's motion during an earthquake matches the building's natural frequency, the oscillations just get amplified. That's when things get pretty dangerous in the real world, because the building starts swaying a lot more than it normally should. That's why damping is such an important part of all this. It helps absorb energy and reduce that motion. We actually see that effect in the math we were doing when we solve the differential equation with a damping term. Of course, our model is obviously simplifying everything a ton. We're assuming the building has uniform material, constant stiffness and damping, and like even evenly distributed mass, while real buildings are a lot more complicated. But this little mock-up, per se, gives us a solid way to understand how exactly these buildings are going to be responding to vibrations and how engineers can look to design them so that they can be as safe as possible.